People who work with statistics and machine learning often run into a recurring problem. What is the best way to analyze a given dataset? By choosing a method that closely models the processes that create the data, it increases our chances of finding a significant result or making better predictions. When you consider that a company may spend thousands or millions of dollars to create a dataset, and you're the one in charge of analyzing it, you best be as prepared as possible to do it. But how can you know what model is best when you don't even have data? The answer is Monte Carlo simulations, which I've previously called the most important skill in statistics. If you're watching this channel, I assume you're interested in learning and doing statistics. By extension, you're probably going to want to know how to do a simulation study too. So in this video, I'm going to teach you everything I wish I knew about simulation studies when I first started as a student. I'm going to guide you through 3 different levels of simulation studies, each one increasing in complexity, and as a result, the things you need to consider when you're developing them. My name's Christian, and this is Very Normal, a channel for making you better at statistics. The best way to do that is to understand the unique and interesting problems that statisticians face. This is one of those problems. To motivate the simulation studies, we'll work through a problem that I struggle with on a daily basis, growing this channel. One of the most important ways to attract attention to your channel is in your thumbnail. Without a good thumbnail, people won't be compelled to click on your video. Let's say that I have 2 thumbnail styles I want to compare, one with my usual style, and another one inspired by popular trends on YouTube. I want to know which one is better, and God, I hope it isn't this one. YouTube lets me run an A/B test which will let me experiment on these 2 thumbnails. Some people will be recommended my video with thumbnail style A, and others will get style B. We'll pretend to do this for a year's worth of videos, about 27 in my case. Since we're considering views, that's a continuous outcome. Comparing things is a classic 2-sample problem. The relevant statistical methods are the t-test, Welch's t-test, and the Mann-Whitney-Wilcoxon test. The problem here is that there's multiple hypothesis tests, and it's not really clear which one will give me the best shot of detecting a significant difference between the thumbnails. This is where the Monte Carlo simulation comes in. If you don't know what a Monte Carlo simulation is, then don't worry. We'll cover it on this first level. In this level, our simulation study is small enough to be conducted quickly on a personal machine, like a laptop or a desktop. The first step in a simulation study is to generate data. Since we're dealing with a 2-sample problem, we need 2 vectors. One to represent the views that style A got over 1 year, and another for style B. For simpler problems, this data usually comes from random number generators that are available in most programming languages. Base R has functions like runif, rbinom, and rnorm that let us sample from the uniform, binomial, and normal distributions respectively. Python has similar functions, but in the NumPy or SciPy libraries, I think. These functions generate data from parametric probability distributions, distributions whose shape change with the choice of just a few numbers, called parameters. This means we can easily tune the random number generator just by changing a few values. According to my analytics, an average video of mine receives between 7K and 14K views a week after being uploaded. To make our simulation as accurate as possible, I want to capture this range when I generate the data. Since I consider this to be a continuous outcome, I'll use the rnorm function. I need 27 simulated values for each vector, so I just need to enter 27 for the first argument. The middle of 7 and 14K is about 10.5K, so I'll use this as the mean of the distribution. If I view 7 and 14K as the 2.5 and 97.5th percentiles of the data, then each of these values are 3 standard deviations away from 10.5K. Working out the math, this means that the standard deviation should be about 1200 views, so I'll use that. Once I run this function, I'll get a vector of numbers that represent a year's worth of views for videos that use style A for their thumbnails. I need to do the same thing for style B, but it'll be slightly different. I'll generate the data such that style B increases the average number of views by 600. If we divide this mean difference of 600 by the standard deviation of 1200, it gives us an effect size of 0.5. This is also known as Cohen's d. Effect sizes are useful here because we're working with continuous data. The scale of mean differences depends on the variance of the data. A 600 view difference when the standard deviation is 1200 looks different than the 600 view difference when the standard deviation is 600. This difference is easier to see when the standard deviation is smaller. Talking in terms of effect sizes allows us to control for the variance in the data and talk in more standardized terms. We'll consider this further in later simulations, where we'll look at a range of effect sizes instead. After generating this data, I need to run a hypothesis test on it. This hypothesis test is the second part of our simulation study, a statistical model that we want to run. What I'm interested in is how well powered a t-test is to detect this specific 600 view difference. In other contexts, this might be a machine learning model. The version of the t-test I want to run is student t-test, the one where you assume the variance of the two groups are the same. Later in the video, we'll include Welch's t-test, which is the one where you assume that they're different. Students often get frustrated with assumptions like this because it's unclear how it will affect the results of the test. While you might be able to figure it out theoretically, a simulation study can give you a more concrete answer, which is what makes them useful as learning tools. Students' t-test can be implemented using the t-test function in R. By default, it uses Welch's t-test, so we need to specify in the function that we want to assume that the two variances are equal. This is done by setting the var equal argument to true. Once the test is run, I can check whether or not the null hypothesis is rejected through the p-value. In this case, it's less than 5%, so we'd reject the null hypothesis. This particular result makes sense because the two groups are actually different, based on how I generated the data. It'll be useful to store the result of the test in its own variable. Depending on how the data is generated, we could get a different result, and we need to account for this randomness, so we need to repeat this three-part process many times. To implement that, I'm going to use a simple for loop to repeat this process 10,000 times. This sounds like a lot, but it'll go by quick, at least in this level. I've already written the code for a single hypothesis test. I can just copy it into the loop. It's useful to work out the steps of a Monte Carlo simulation before you actually run the for loop, since it's easier to debug. The only thing I need to add is another data structure to hold the results of all the simulations. I'll initialize a vector outside of the loop and then index the specific position in this vector based on the current replication number. Power is the conditional probability that we reject the null hypothesis, assuming the null hypothesis is wrong. This is exactly how we generated the data, so if I calculate the proportion of simulations that reject the null hypothesis, then I'll get an estimate for how powerful the t-test is in this specific situation. This follows from the law of large numbers, where a proportion of events will converge to the true probability of the event if we have a large number of trials. This is the core reason why we need to generate such a large number of simulations in the for loop. By itself, this number really isn't that useful. The goal of our simulation study was to compare hypothesis tests, so that we could see which one had the highest power in situations that matter to us. So in the second level, we're going to move towards this goal and lay the mental groundwork for how to do simulations at a larger scale. In its current form, my code stores all of the results into a vector that we can use later to estimate power after the replications are finished. But consider the fact that our simulations will be deleted if we either close our studio or if it crashes. So if we lose our results, we'll need to run the simulation again to get them back. This is a problem, and it would be better to incorporate a way to save our results as they're finished. Second, now that we have multiple hypothesis tests, we need another layer of iteration to account for each test. 3 hypothesis tests and 10,000 replications each equals 30,000 replications in total. This is still doable on a personal computer, but we could benefit by adding some more structure to our code. By doing this, we'll gain access to more sophisticated ways to run it. I'm a huge fan of the tidyverse, so I'm going to organize all of our simulations into a tibble. I'm going to use the expand grid function from the tidier library to do this. I'm going to pass in 2 vectors, one containing the strings to represent all the hypothesis tests I want to run, and another vector that numbers all the replications we want to do for each test. What expand grid does is that it takes all the vectors in it and creates a new tibble that contains all the possible combinations of the vectors within it. Therefore, each row in this tibble represents a single replication we need to perform. Since this is a tibble, we can add more columns to the tibble to make simulating a little smoother. I'm going to create a new column called file name that combines the test and replication number together to form a new string. I'm also adding an RDS extension at the end. I'm adding this because I plan to use these strings to save each replication with a unique name. Next, I'm going to add another column called seed. Because Monte Carlo simulations rely on random number generators, we'll get a slightly different result every time we run the code. This seed will make sure that the generated data will be the same no matter how many times I run the code. I'm just going to use the row number function to index each row, and this number will act as the seed. And this is all we need to set up the simulation. The idea now is to iterate over the rows in this tibble and use the unique values in each row to produce a replication. The way we'll do this is through the pwalk function. Pwalk lets us apply a function to each row in the tibble, using the values of the columns as arguments in the function. You may have heard of its cousin, map. Pwalk is preferred here because we don't need to store all the simulation results into this single tibble. The first argument of Pwalk takes a list, and within this list, we need to supply all of the columns we want to use, which in this case are the name of the test, the file name, and the random seed. Next, we'll supply the function we want to apply to each row. Instead of writing it directly within Pwalk, I'll write it separately to make the code a bit cleaner. I'll name this function run replication, and it'll take 3 arguments, test, file name, and seed, to match up with the columns we chose earlier. The function code will look similar to what we made in the first level, but with a few key differences. First, we're going to use the seed in the setSeed function so we can control the randomness. Then I'm going to generate the data similar to what we did in the first level. I'm using the string in test to change which test is used on the data. Afterwards, I'm storing the results in a list, which I then save to an RDS file using the save RDS function. Since I'm already saving the result, I don't need to return anything. Now that the function's been made, I can just stick it into Pwalk. Notice that you don't need to show the arguments of the run replication function here. We're not running the function, but rather we're passing in the function itself. We could just do all the simulations now, but I'm going to teach you a lesson first. With large-scale simulation studies, it's always good to do a test run first. I'm going to change the number of replications to 10 just to make sure that all the code is working. If we run this and look at the folder that contains our R project, you'll see the results of all the simulations. There's a lot, but each of them are relatively small. Since we're going to be dealing with thousands of simulations, it's probably better to store them in their own directory. So I'll make a new folder and place all those simulations inside it. I'll go back to my table of simulations, set the number of reps back to 10,000, and add the directory right into the file name. But wait, remember that I did that test run earlier. I left those initial simulations as a teaching point. If I were to run the simulation again, our code would rerun these replications, even though they've already been done. In this particular example, it wouldn't take that much time to run, but for your own simulations, a single replication might be really time-consuming, on the scale of minutes. It would be better to implement a check so we don't redo work we've already done. If the file name for the replication is already in the directory I created, then we return out of the function. If not, we'll continue to do the rest of the code. This solves our saving problem, but in its current form, our simulation is still sequential in nature. What we want is for these replications to happen in parallel. Thankfully, there are a lot of mature packages in R that make parallel computation easy. The package that I'll be using is the fir package, which is an analog to the pur package found in the tidyverse. Pur provides packages like map and Pwalk, which allow us to apply functions in a row-wise manner in a tibble. What fir does is that it enables all of the functions in pur, but allows them to be done in parallel. Instead of Pwalk from pur, I'm going to use future Pwalk, which is from fir. The code will work exactly the same it did before, but it'll be done in parallel, after we make a few adjustments. Before we run future Pwalk, we need to tell R exactly how we want to do the parallel computation. We do this through the plan function, which comes from the future library. In plan, I'm going to write multi-session here. Multi-session means that I want to create several R sessions that can be used to do simulations. There are other alternatives we can write, but multi-session will serve our purposes here. Next, I need to specify how many cores in my computer I want to dedicate to the parallel computation. Usually you dedicate as much compute power as you can, but since I'm doing other stuff on my computer, I'm just going to allocate 4 workers to do the job. If you run this, it looks like nothing happened, but RStudio is ready to do the parallel computation. We're finally set up to run this full simulation, and with the power of editing, make it seem like it instantly happened, but in reality it took a few minutes. Since the results are all in this directory, I need to read in all the individual results and collect them into a tibble. Overall, all the tests achieve similar power for detecting an effect size of 1/2. The Mann-Whitney-Wilcoxon test is slightly less powerful, but it's not really that big of a difference. If we were to pick one based on the simulation alone, you'd probably just go for Welch's t-test, but I want to hold off on making any conclusions for now. And there you go. In the second level, we increased the complexity of our simulation by incorporating all 3 hypothesis tests. This resulted in a larger scale simulation study. To summarize, we created a tibble to keep track of all the replications, we switched our iteration mechanism to PWalk to prevent crashes in our studio, and to organize our simulating code into its own function. We added a saving and checking feature, and we incorporated parallel computing to make our simulations much faster. If you're just interested in making your own simulation studies, then I think that level 2 will be enough for most of you to explore your own curiosity. But maybe you're someone who needs to do some hardcore, large-scale simulations, like a researcher or someone in industry. Well, what could possibly make a simulation study be that large? It's the sheer number of ways that we can generate different combinations of data and models. Piling around a specific change in views is making a huge assumption about future data. In reality, we usually use a range of different and meaningful effect sizes that we would expect for our specific problem. I'm a small YouTube channel, so a 600 view improvement just for changing a thumbnail might be worth it for me, but these would be peanuts for a larger channel. There's a difference between statistical significance and practical significance, and you want to plan your simulations around the latter. So I'm going to add 2 more effect sizes to my simulation, view changes of 300 and 900, which correspond to effect sizes of 1/4 and 3/4 respectively. In addition to these effect sizes, I'm going to add another probability distribution. Currently, I'm only using a normal distribution to generate the data. The problem with the normal distribution is that outliers are inherently very rare. But on YouTube, videos can go viral, resulting in views that are orders of magnitude greater than what your channel usually sees. Conversely, channels might put out a video that not even their most loyal audience is into, resulting in much less views. That is, the normal distribution might be inadequate for capturing all the inherent complexities in this type of data. My simulations could be more realistic if I accounted for this in the data generation. I'll also generate data from a Cauchy distribution, which are still bell-shaped, but the probability of seeing an outlier is much higher compared to the normal distribution. In fact, outliers are common enough such that Cauchy distributions don't have averages. They do have medians though, so I'll take advantage of that. When I'm using a Cauchy distribution, I'll generate the data such that there's a median shift of 300, 600, and 900, analogous to the mean shift in the normal. So there are 3 different effect sizes and 2 distributions to pick from. Each combination of effect size and distribution needs to be run with each hypothesis test, and each of those combinations need 10,000 replications. In total, we need 180,000 replications. No matter how you spin it, that is a lot of replications to run. It's usually unfeasible or too time-consuming to do a simulation study of this scale on a personal computer. Take it from me, who once in the past chose to wait 2 weeks for a simulation study to finish, essentially wasting my time in the process. At this level, we need a high-performance computer, or HPC for short. For the purposes of this video, I'll be using it to refer to a cluster computer. Like its name suggests, a cluster computer is a group of computers that work together as a single unit. In addition to these computers, there's usually some sort of software that helps to coordinate how work is distributed to the individual computers in the cluster. Most of you won't have easy access to an HPC, so I totally understand if you click out of the video at this point, but if you're interested in learning more, let's get to changing the code. But first, an honest aside. This level is right at the limit of my knowledge. What I talk about here are things I've learned from teaching myself how to do these things. I'm only familiar with the system my school uses and what software is on it, so your experience may vary based on what's available to you. My hope is that the general concepts I talk about will carry over to what you have. I say all this because if you're more experienced with this and there's something I can do to improve this process, then please let me know in the comments. The first thing I'll do is take the code from the second level and put it in a script. We need to send this code to each of the computers in the HPC, so a script is the most efficient way to do this. Notice that I've added all the parameters into the file name column so that each permutation gets the correct number of repetitions. I've also added these new columns into PWalk. I've also made adjustments to the run replication function to account for these new columns as well. But we have a problem. If I send this code to the HPC in its current form, then each machine will be duplicating all of these replications. Not good. We'll approach this problem with a mental model. Imagine 2 computers. Let's call them Machine 1 and Machine 2. We need to be able to send the same code to both of these machines, but have them work on mutually exclusive sets of replications. The good thing about this mental model is that it doesn't matter if we have 2 or 100 computers in the cluster. The essential problem remains the same. A key fact we need to assume is that we can check for the ID of each machine in our code. That is, I need some code that will return 1 if it's run on machine 1, and 2 if the code is run on machine 2. The function that can do this is the sys.getEnv function. This function retrieves values for environment variables whose values are set outside of a program, on the machine itself. It just so turns out that the machine quote-unquote ID is one of those environmental variables. For our simulations, the specific environmental variable we need is slurm array task ID. I'll get back to this in a bit, but just know that I can run this function on both machines, and the result will be what I want. With this new variable in mind, we can create a new column in our tibble to help each machine pick its own set of replications. Finally, I can use the filter function to filter down the tibble to all the rows where the machine column matches the machine ID. And to be honest, that's all we need to run the simulation code. But coding was probably the easiest thing about this level. The difficult part is actually doing everything on the HPC itself. If you've only run code on your own computer, then you're probably used to working with just a graphical interface like RStudio. But when you're working with an HPC, you're most likely going to have to interact with it through a command line, like terminal or command prompt. If you've never done this before, you'll need to learn some basic actions on the command line before you start. This isn't the video to do that, but if you can understand what these commands are, then you should be okay to proceed. To get access to an HPC, you'll most likely have to contact the group that controls it at your school or company. More likely than not, you'll probably have to fork over some money to be able to use the compute resources, so be aware of that. After that's all settled, you'll be given some login credentials, which you can use to log into the HPC through the SSH protocol. Once you're logged in, you'll be brought into what's called the login node of the HPC. A node is just a physical machine in the cluster. Within the login node, you can lightly edit files and submit jobs that will be sent to parts of the HPC dedicated to more hardcore computation. If it's your first time on the login node, then nothing will be on the computer. You can check the contents of your current directory with the ls command. I've used this account before, so some of my previous work is here, but it should be empty for you. The first step in running our simulations on the HPC is to actually get our code on it. Although we can do this from the command line, I prefer to use a free open source tool like FileZilla because it provides a graphical interface for transferring files. You'll need to give your login credentials so that FileZilla can also see inside the HPC, but once you're inside, you'll be able to see the contents of both the HPC and your own personal computer. Here I'm in the folder that contains the code I wrote earlier. I can click and drag it into the login node to begin the transfer. Once the code is in there, we can recheck it to make sure that it's in. But like I mentioned earlier, we don't run simulations on the login node. We need to tell the HPC that we'd like to use some of its resources so we can do that. I need to talk to the software that coordinates all the work done on an HPC. In my case, that's Slurm, short for Slurm Workload Manager. Slurm is what's called a job scheduler. Its function is to provide users a way to submit work to the HPC and to allocate the resources of the HPC in an efficient way. We need to submit what's called a job to Slurm, which describes exactly what we want from the HPC in terms of time and computational resources. There are different ways to submit a job to Slurm, but I'll opt to use what's called a batch script, where I can write my job details in a text file and then give this file to Slurm. I don't currently have a batch script, but I can quickly write one using the vim command. If I type vim job.sh, then the command line will create a file with the same name and open up a text editor that will let us change it. The sh extension indicates that the file is a shell script, meant to be run on the command line. The first line in the file needs to look like this. It's called a shebang, and it indicates what kind of interpreter should be used to run the script. In this case, it tells Slurm that we need to use the bash shell. Afterwards, we're going to give specific instructions to Slurm, which start with the £, followed by the word sbatch. What follows after sbatch are parameters which specify the resources we want to use. There are a lot of different sbatch parameters, so I'm just going to list the ones that I use the most with my own simulations. First is job name. This lets you give the job a particular name, and it's helpful in distinguishing between different jobs you might need to run. The account parameter tells Slurm which account on the HPC should be charged for using its resources. Slurm has built-in ways to communicate to you about the status of your job. The mail type argument specifies when Slurm should send you an email. In this case, it's set to end, so Slurm will send you an email to the email in the mail user argument when the job is ended. The time argument describes how long the HPC should run your job before terminating. Here, it's written as 12 hours. If your job finishes before this amount of time, then you'll just be charged for whatever time is used. In an HPC, there may be certain nodes or sets of nodes that are specialized for certain tasks or resources. These are called partitions, and you usually need to specify what partition your job should be run on. The name of the partition you should use will depend on your HPC, so make sure you gather that information too. The array argument tells Slurm that I want to set up an array job. Array jobs are a way to efficiently schedule many similar jobs at the same time, which make them perfect for Monte Carlo simulations. That is, I'm telling Slurm that I want 100 simultaneous jobs, and that I want to give each of them an ID from 1 to 100. And if you remember what I wrote in my simulation script, it's the number that I'm referencing with the Slurm array task ID environmental variable. The nodes and the CPUs per task arguments describe different aspects of how much computational resources you want for each job in the array. Emphasis on each. Not remembering this is an easy way to blow up your bill. If you're new to this, you may not even know how many resources you'll need, so I'd recommend working with the HPC admin to get some tips. One thing to note about an HPC is that they can handle a wide variety of tasks, involving many different types of software, or modules. Unlike with your personal machine, these software are not immediately usable by the nodes. In my batch script, I need to specify what modules should be used with our job. In our case, we're using R, so I need to include the R module with this line here. The specific version might be different, depending on when you watch this video. And finally, we need to tell the script that we want to run an R script. After writing all this, we need to press escape to get out of writing mode and type :WQ to write to the file and quit out of Vim. With the ls command, we can check that both the simulation script and the shell script are there. To run the shell file, we need to use the sbatch command followed by the name of our sh file. If I run this, we'll be given a job number. You can use this number to check the status of your job via the sq function with the j flag. After this, it's just a lot of waiting. Go outside, touch some grass, enjoy nature, or be like me and play Super Auto Pets on the sofa until it's done. You should be able to look in the FileZilla and see all the simulations in the folder you created to hold them. Before you download them from the HPC, it's always a good idea to zip them up into one compressed folder. Finally, after this long journey, we can analyze the results. You can see that power increases as effect size increases. That's something we'd expect because it's easier to resolve the view distributions of the two styles. But look at which tests behave best depending on the distribution. When the data is normal, the t-tests perform better, but the reverse is true when the data is Cauchy. These outliers threaten the assumptions of the t-test, and a consequence of that is severely reduced power. Based on these findings, I would be more inclined to use the non-parametric test to analyze my future YouTube data. This concludes my crash course on Monte Carlo simulations. I hope you liked the video. It's a lot longer than my past videos, but it contains all the painful lessons I've learned doing them during my PhD. I wasted a lot of time and effort learning through trial and error, so I hope that I can help you on your own journey if you've made it this far. If you found this video useful, I hope that I've earned a like and a subscription from you. I try to make statistics every 2 weeks, even though I failed here, but if you'd like to hear about videos as soon as they come out, you can also subscribe to this channel newsletter. You'll get videos sent straight to your inbox, and you can learn a little bit more about what's going on with me behind the scenes. That's it for this one. I'll see you in the next one.